back, dear students, for the pre-stressed concrete design. Today's class we will discuss on the time dependent losses in pre-stress. The first one, that is loss of pre-stress due to creep in concrete. That is, first you need to understand what do you mean by creep in concrete or creep of concrete. It is a time dependent increase of deformation under sustained load. That is, due to a sustained or permanent load, there occurs some deformation in the concrete member, and that deformation that occurred in the concrete member is called as creep of concrete. Due to this creep, the pre-stress in tendon decreases with time. That is, the pre-stressing force in the tendon decreases due to this creep. That is, there occurs relaxation. Due to the deformation of the concrete, there occurs relaxation, and as a result, the tendons will also relax, or tendon will also reduce its length. As a result, there will be the decrease in pre-stressing force. The factors mainly affecting the creep as well as the shrinkage of concrete are the age of the concrete, the applied stress level, the density of the concrete, the cement content in concrete, the water cement ratio, relative humidity, time, temperature, etc. This we have studied in your concrete technology, so I am not going in detail of this. If you want, you can refer some concrete technology textbooks. You can understand this in deep. We will mainly cover the aspects of this creep in pre-stress concrete. So you can see this loss of pre-stress due to creep in clause number 19.5.2.1 of your IS 1343/2012. So the initial pre-stress is stress in tendon gradually reduces due to the creep of concrete. So the method used to determine this creep or loss due to creep in concrete is creep coefficient method, which I'll explain you. Coefficient method. So in this method, we need to first understand what do you mean by creep coefficient. Creep coefficient is denoted by phi naught, which is equal to creep strain, that is a strain due to creep, divided by elastic strain, that is your normal strain due to the elastic shortening. That is, I can represent it by epsilon c divided by epsilon e. Now, which means from here I can write epsilon c, that is creep strain, is equal to creep coefficient phi naught into epsilon e. So now the loss in pre-stress due to creep, the loss in pre-stress due to creep is equal to the strain or the creep strain into Young's modulus of steel. That is the basics I told you. Except for friction, all the losses is equal to the strain into Young's modulus. That is a stress loss in pre-stress is equal to strain into Young's modulus. So I can write here the creep strain as phi naught into epsilon e into es, isn't it? So this epsilon e is the strain or the creep elastic strain in concrete. That is, I can write this as phi naught phi naught into epsilon e. I could write it as what? Epsilon e is equal to, that is strain in elastic strain in concrete. I can write it as stress by Young's modulus of concrete, that is Fc by Ec into Es. That is, I could write this one as phi naught into Fc into M, where Fc is the stress in concrete at the level of steel. So the loss in pre-stress due to creep is equal to phi naught into, that is creep coefficient into stress in concrete at the level of steel into modular ratio, that is Es by Ec. So this term is the only unknown, that is your creep coefficient is the only unknown term, and that can be easily found out by your IS 1343/2012. It gives the creep coefficient phi naught for 70 years of an ordinary structure concrete after 70 years of loading. That is based on the age to loading to days, how much days it is being loaded, and for different relative humidity condition, because the relative humidity, based on the relative humidity, this will change. So based on the relative humidity conditions, and notional size. I will tell you what is the notional size. The different creep coefficients are given, that is page number 6 of your IS 1343-2012. You can see this, where AC, in order to find the notional size, AC is the cross-sectional area, U is the perimeter of the member in contact with the atmosphere, and RH is the relative humidity. You could find out for different ages of loading, you could find out the creep coefficient, okay, based on the notional size. So once you do this, you will get the notional size, and if it is in between, you can interpolate this. So this is creep, loss due to creep. Now once we do the numerical, it will be more clear in this. The next one is loss in pre-stress due to shrinkage of concrete. You can see in clause number 19.5.2.2, due to shrinkage of concrete. So the shrinkage of concrete is due to the gradual loss of moisture which result in change in volume. That is, there will be some strain occurring due to this change in volume. So the shrinkage strain, that is, we are denoting it by epsilon s, epsilon cs, comprises of two components: the drying shrinkage epsilon cd and the autogenous shrinkage epsilon ca. That is, in your concrete technology you might have studied, there are four types of shrinkage, that is autogenous shrinkage, drying shrinkage, plastic shrinkage, and carbonation shrinkage. So mainly in structural criteria, we mainly consider this drying shrinkage strain and autogenous shrinkage strain. This autogenous shrinkage strain, or the total shrinkage strain, I can write it as epsilon cd plus epsilon ca. The autogenous shrinkage strain develops immediately after the hardening of the concrete. That is, within 28 days of your concreting, during the hardening of the concrete, this autogenous shrinkage strain occurs. And this drying shrinkage strain is mainly after the hardening of the concrete, develops due to the lifetime of the structure. That is, from the capillary and from the inside of this molecules, concrete particles, the water will get evaporated, or water will get lost by some means, and there occurs some shrinkage of concrete, and there is drying shrinkage. And autogenous shrinkage occurs during the loss of water during the hydration of the concrete. So the total shrinkage, I could tell it as it's due to the drying shrinkage and autogenous shrinkage. And I could write the loss of stress due to shrinkage, I could write it as loss of stress due to shrinkage is equal to epsilon cs into Young's modulus of steel, that will be the loss of stress due to shrinkage. Now this epsilon cs value can be found out from your IS 1343. We will discuss that in detail while we are doing the numericals, because it depends on many factors. So that we will discuss while we are doing the numerical. Now the next one is loss of pre-stress due to relaxation of steel, or it is also called as creep in steel. That is, relaxation of steel means it is the size of the steel is reducing, or it is also called as creep in steel. It is seen in clause number 98.5.2.3. You can see, when a high tensile steel wire is stretched and maintained at a constant strain for a longer time, the initial force in the wire does not remain constant but decreases with time, and that is called as your relaxation of steel. This decrease of stress in steel at a constant strain is termed as relaxation. And the factors affecting relaxation are the time of this stretching, the initial stress applied, the temperature, and the type of steel being used. So the relaxation loss is directly given by your IS 1343 in table number 6, based on the characteristic strength of the precessing steel. At this value is corresponding to the relaxation loss in percentage at 100 hours after tensioning and at a mean temperature of 20 degrees Celsius, 20 plus or 2 degrees Celsius. And the initial stress, if you are getting this value, you can find the relaxation for normal relaxation and low relaxation. These two values, based on the question, you can answer these two. So this is what the losses in pre-stress, that is the 6 losses, that is immediate loss and time dependent loss. And now we will discuss on the numerical part of these losses.